Okay, you all welcome to Mechanical Principle lecture series. Today we are going to discuss about the buckling load analysis. Okay. So buckling is a failure method, the failure method of columns under critical loads. Okay. So this will happen below the ultimate compressive stress. So that's why that is very important to analyze this one. Okay. Then here we are going to derive this buckling load equation, Euler buckling load equation, and also we are going to discuss what are the factors affecting to the critical buckling load. Okay, let's move to the today's lecture. In this lecture, we are going to discuss about the buckling analysis. Okay. Then if we take a certain slender element, let's take this the one of the element. Okay. Let's take this element, let's take the uniform cross section bar element is subjected to a tension. This kind of two forces acting in the two end of the beam. Okay. Then what is the how if this element is failed due to this tension, what is the method it failed? How can it fail? Due to exceeding the tensile stress. Due to exceeding the ultimate tensile stress, it is subjected to a tensile failure. We are calling it as a tensile failure. Okay, it start happening at beyond the yield point. Okay, it is beyond the yield point when increasing this F force gradually beyond the yield point. Let's take this the ductile material. Beyond this yield point, the permanent deformation occur. Okay, permanent deformation occur. Okay, then this is one of the method to fail this when it reaches to a ultimate tensile stress. Then it is suddenly reduce its strength capacity. Then it will fail due to exceeding the ultimate tensile stress. This is a method of failing component by axially loaded component by tension. Then what happens if the component is subjected to a compressive stress? Okay, let's take this the uniform cross section bar element subjected to a compressive stress. Okay, compressive load is acting on it. Okay, compressive load is acting. Stress. It is subjected to a compressive stress due to acting of these forces. Then what are the how if this structure fail, if this beam is failed due to the compressive stress, okay, when increasing the load, what are the method to fail this component element? Okay, there's a two method to fail this component. The one is due to exceeding the one method is due to exceeding the ultimate compressive stress. Okay, this material having certain compressive stress limit. Beyond that limit, it will fail due to crushing. Okay, due to crushing, it will fail due to crushing. Okay, due to exceeding the ultimate compressive stress, it will crush and fail. Okay, it's a one of the method. Then there's another method to fail this component called the buckling. It is very important. Then this structure, when taking this load, structure deviate from its stable position. Okay, this is the stable position. Vertical position is the stable position. It deviate from the stable position and forming this kind of buckle. Okay, when gradually increasing the F, when it reaches to a certain critical limit, when the F force reaches to a certain critical limit, this structure suddenly deviate from the stable position. Then it will buckle, forming this kind of curvature. Then it's no longer support this load. So whatever, it suddenly collapse. Okay. Then this is called instability failure. This failure occur due to deviate from the stable position. Okay. then this will happen before the compressive failure. That means for certain structure, the compressive failure limit is 1000 kilonewton. Let's assume this will happen less than the 1000 kilonewton. Less than the 1000 kilonewton. Before reaching to the ultimate compressive stress failure limit, this buckling failure will occur. So that is why this buckling failure is important in structural mechanics, because it failed before the compressive failure. That means the structure cannot take the ultimate load. Okay, so then this will happen mostly in axially loaded component, especially in columns. Okay, not only in the columns, it also happen in the truss structures. For example, if you take the truss structure, this kind of truss structure, okay, let's take this is the truss structure. You know, in truss structures, all the forces are acting along the truss bar elements. Let's take this kind of a vertical load is hanging on this node. Okay, P load. And let's take another roller support in here. Okay, yeah. So then what happens if we take this structure? These elements are subjected to a compressive stress. These are subject to a compressive stress, while these are subject to tensile stresses. These are subject to tensile stresses, and here also subjected to compressive stress. Likewise, then here also subject to a compressive. Then this is subjected to tensile. Okay. Then there's a possibility to this compressive the bar element, that means bar which acting the compressive stresses cause to buckle. There's a possibility to cause the subjected to a buckling failure. So that means when it reaches to a critical limit, it will buckle forming this kind of curvatures. It will buckle forming this kind of curvature. Then this entire structure collapse suddenly due to this buckling of one of the element. Okay. Then to avoid this this kind of buckling in truss structure, this kind of additional support members are added into the structures. Additional support. So that means this will give lateral support to this bar element. Then will the strength increases. That means the buckling load can increase by giving the lateral support. Later we are discussing this one. Then you may, in most of the cases, this kind of idler bars are inserted to this kind of truss structure to strengthen the structure against the buckling failure. Okay, this will happen in this kind of truss structure and also the vertically loaded column. Okay, column structures. No matter it's a material, it will happen in a concrete structure and also the steel structures also. Okay, so then this is the introduction to the buckling analysis. Then let's see what are the factors affecting to this buckling. Okay, that means first of all, let's take the situation if certain structure starts its buckling. That load we are calling it as a critical buckling load. Critical buckling load. Okay, for a certain structure, when it reaches this critical buckling load, it will buckle. Okay, it will fail due to buckling. Then this is called the critical buckling load. The maximum load it can take before buckling, we call it as a critical buckling load. Okay, then let's see what are the factors affecting to this critical buckling load. Okay, what are the factors affecting to this critical buckling load? What are the factors affecting to this critical buckling load? Okay, let's move to next one. Okay, let's take first one. We are going to identify what are the factors affecting to critical buckling load. What are the factors affecting to the critical buckling load? Okay, Yeah, actually, there's a three factors affected this buckling load. Let me explain this one. In a general sense, let's take two different elements. One is too lengthy, the one is very short. The cross section is same, cross sectional area is same, and also the second moment of area, distribution of the area also same, and also the elastic modulus of the material and the material properties also same. All the material properties are same. The E, elastic modulus of the material, and also the same material. Let's assume same material. Then let's take this is pin supported. The support conditions are same for both the structures. Support conditions are same for both these structures. Then let's take the two forces acting. Forces acting. The F force. Gradually these increasing, these two. Then only difference is L1 and L2. L1 is greater than L2. Okay. L1 is greater than L2. So what can you say about the buckling about this structure? Which one buckle first? Which one buckle first? This either this lengthy one or shorter one. In general sense, we can say so lengthy one there's a more possibility to fail due to buckling. Okay, lengthy one there's a more possibility to fail due to buckling for me this kind of curvatures than shorter one. Okay, in a general sense we can say. Okay, so that means this critical buckling load, we can say critical buckling load is inversely proportional to the length of the element, length of the column. Let's take the, we don't know what is the exponent. Let's take the exponent as x. Okay, exponent as x. General sense we can say that one. Okay, then let's take another situation. The same dimensions, the cross sectional area, length also same. In this situation, length same, the cross sectional area also same. Okay, cross sectional area also same, and also the support conditions are also same. Support conditions are also same. The two different forces acting on it, F1, F. So only difference is the elastic modulus of the material. External, all the dimensions are same, the support conditions are also same. Only difference is the elastic modulus of the material. This one having the E1, this one having the E2. E1 is greater than E2. Let's take E1 is greater than E2. That means this material is rigid than this material. This material is rigid than this material because E1 is greater than E2. Okay. When the material is more rigid, mean it is a resistance to buckle. Okay, what can you say about the buckling load in this situation? Which one having the greater buckling load? Okay, we can say this one having the greater buckling load because it's rigid than this component, so it is resistant to buckle. So we can say critical buckling load is proportional with the elastic modulus of the material. Okay, elastic modulus of the material. Okay, third parameter. In this situation, the same amount of material, let's take this is the cross section of a let's take this is solid, then this is the hollow, but same amount of material, same weightage, and also only difference is this material cross section has distributed away from this axis. You can see the same cross sectional area, but it is distributed away from this axis of the column. So that means I value I1, I2, I1 is greater than I2. In this situation also, let's assume we are testing this two specimen, the same support conditions, and we are applying the load to the component F and F. The which one fail first? Which one fail due to buckling? Okay. Then this structure can take more load against the buckling because it is spread. this area has spread, is in a general sense we can say it is resistant to buckle. It is resistant to buckle in general sense. Is a here it is a cross section is a cross sectional area is same, but only difference is it is distributed away from the axis of the beam. That means is I2 is here. Yeah, sorry. I2 is greater than I1. I2 is greater than I1. Then this structure having the higher buckling load than this structure. Then we can say another relationship. Critical buckling load is proportional to the I value. Proportional to the I value of the structure. Let's take this is a component as Z, and this is let's take the Y. Okay. Then here we have defined three different situations we considered. These are the factors affecting to the buckling load. Then all of these three relationships we can combine to form one single equation. Then let's take the equation 1, equation 2, equation 3. From equation 1 and 2 and 3, from equation 1, 2 and 3. So we can combine these two equations to form the equation, the critical. So I'm going to multiply with the constant, the K, E into Y, I into Z, into L into X. This is the basic relationship for critical buckling load. Actually, these X, Y and Z we can determine using by equating the dimensions, and also various methods we can use to that one. I will directly, by equating the dimensions we can determine the X, Y and Z. So I will directly write this equation. For this one, if critical buckling load is equal, here the phi square EI divided by L square. This is the equation given the critical buckling load. You can see the critical buckling load is a function of three variables of the structure. What are these three variables? Is a function of elastic modulus of the material, and also the second moment of area of the material, and also the length of the material. Okay. Then when increasing the length of the beam column, there's an exponential decrease in critical buckling load. Here, del to the power square. So there's an exponential decrease in critical buckling load. The length is the very important parameter when designing a structure against the buckling. And also another important one is the I value. Without wasting the material, we can easily increase the I value against the buckling. Okay, that is very important when designing the structure against the buckling. Then elastic modulus, when selecting the material for a certain column, that is very important to decide this E value, elastic modulus of the material when designing the material column against the buckling. Then this is the equation to determine critical buckling load for structure. If you know the length of the column and also the cross-sectional second moment of area, and also the material property, elastic modulus of the material, we can determine the critical buckling load. Then we can say at this critical load it will fail due to buckling. Okay. Then same equation we can obtain using the basic mechanics theory. Okay, solid mechanics theory. Let's see how to obtain this equation using the basic mechanics theory. Okay, let's see how to derive this buckling load equation from the basics solid mechanics theory. From the basic solid mechanics theory, let's take the certain structure. Let's take this kind of structure. Then when it is subjected to a load, let's take this equation we are going to derive considering the both end pin supported situation. Okay. Then when increasing the F load, when it reaches to critical buckling load, let's assume this structure fail, will start buckling, forming this kind of curvature. Yeah. When it reaches to a critical buckling load. Okay. Then so I will draw the neutral axis of the column to that will easy to calculate the for this calculation. Let's assign the coordinate system also. Here y, here x. Okay, so I will directly draw the neutral axis. Here this is our y axis, this is our x axis. Okay, then let's take I will enlarge and draw this one. This is the neutral axis of our column. I will enlarge and draw this one. This is our column. Okay, let's assume when it reaches to a critical buckling load, when the structure reaches to a critical buckling load, let's assume it will form this kind of curvature before fail. Okay, then let's take the radius of the curvature as this kind of point. The radius of the curvature r radius. So then let's take the r theta coordinate system we are going to assign. Theta we are going to measure in this direction. Let's assume let's take this kind of point. Yeah. So this angle, let's take theta. This angle, let's take the d theta. Okay, d theta. Yeah. Then this arc length, let's take this arc length as ds. This arc length as ds. Okay, arc length as ds. Let's take this angle tangent as this angle is equal to theta. This angle is equal to theta. Okay. Okay. Then we can write this equation. Then we can write the equations. R theta. Here this radius is equal to r. R theta is equal to ds. Okay, by dividing r d theta, no, r d theta, sorry, r d theta is equal ds. I'm going to divide the equation by ds by making d theta divided by ds is equal 1 over r. Let's take this equation as equation 1. Okay, let's take this equation as equation 1. Okay, then using this triangle, let's take using this triangle, let's take this this length as equal to dx. This variation of the deviation due to the dx length along the beam is taken as the dy. Okay, using this triangle, let's take this is the length along the column dx. Then when for the dx length, the deviation of the difference of the deviation, let's take it as the dy, lateral deviation. Okay, so then we can say here this angle is theta. Tan theta we can write tan theta is equal dy divided by dx. Okay, dy divided by dx. So then this equation I am going to derivate with respect to ds. But in this variable, the variable is the theta, so we can't derivate with respect to ds. Instead I will first of all I will write that one, tan theta ds dy over dx ds. Okay, in this situation the variable is the theta, so we can't derivate it with respect to s. Instead we are derivating theta then multiplying with theta. So then what is the derivation of the tan theta? Sec square theta. Okay, sec square theta d theta divided by ds is equal d2y dx square into dx divided by ds. Okay. Then the further we can simplify this equation here. Sec square theta, from this equation 1 over r, so I'm going to put d theta divided by ds from the equation 1. From equation 1 I'm going to, instead of d theta divided by ds, I'm going to do 1 over r. So then we can write this equation, sec square theta 1 over r is equal d2y dx square dx divided by ds from this triangle. What is meant by this one? Dx divided by ds. Dx divided by ds means cos theta. Okay. By making the 1 over r into subject, we can write 1 over r sec cube theta, d2y dx square 1 over sec cube theta into cube theta. Okay. Then I'm going to take this calculation to here. Okay. Then we can write 1 over r is equal d2y dx square. Then 1 over sec square theta. We can write this equation, sec square theta into 3 over 2. Okay, 3 over 2. Okay. Then what is sec square theta? In the trigonometry, you know the sec square theta is equal to what? Dx square 1 plus tan square theta. Okay, in trigonometry, you know this one. Okay, 3 divided by 2. Okay. Then what is tan theta? Tan theta dy over dx. From this equation, tan theta is equal dy over dx. Okay. So I'm going to put this in here. 1 over r is equal d2y dx square 1 divided by 1 plus dy over dx into square into 3 over 2. Finally, we are obtaining this equation. In this equation, you can see dy over dx. What is the dy over dx? This deviation with respect to the length of the column. Okay. Actually, in the real situations, this deviation of the column before it fail due to buckling is very small compared to the length of the column. Okay, compared to the length of the column, this deviation before it fail due to buckling is very small. So this ratio is very small. dy divided by dx is very small. So when taking this square, that is also very small. So we can equate this one to 0. So then finally we end up with this equation. Let me write that equation. 1 over r is equal dy over dx square. This is the equation. Let's take this equation as equation A. Okay, I think you all got a very clear idea how to obtain this equation. Okay. Then let's obtain another equation, then we can combine these two equations to form the buckling load equation. Okay, then another equation we are going to obtain, then we can combine these two equations to form the buckling load equation. So let's take, so I'm going to section somewhere in here. I'm going to section this, let's take this is the center of the arc. So I'm going to section somewhere in here. So let me draw the free body diagram of this separate beam part. Then I will enlarge and draw that one. Sorry, I enlarge and draw that one. This is the beam part. Okay, this is the beam part. Then let's take the center. Then this is the neutral layer. You already know what is mean by the neutral layer. We discuss bending stress, so you know that one. Let's assume this is the coordinate system, this is the y, this is the x, this is the x. Then according to this position, also I'm going to just take d theta, then let's assign the coordinate from here y dash, here x dash. The another coordinate system we assign by taking this point as the center. Okay, then actually this calculation you already know, because when we are discussing the bending stress formula, the same calculation we did. So I'm repeating in here that one. Okay, then if you take the certain layer away from the y dash distance from the neutral layer, so I will enlarge this area to show that one. Okay, and this is the neutral layer. Let's take another layer which is away from the y dash distance from the neutral layer. Okay, y dash distance from the neutral layer, we already know on the neutral layer there's no compression or tension. Okay, so then we are going to find the strain developed in this layer. What is the strain developed on this layer? Okay, what is the strain developed on this layer? How to calculate that one? What is the original length of this layer before it buckle? This is the original length. This is the original length, because this neutral layer is not subject to any deformation. So the before it buckle, having it when it in vertical position, let's take this is the A, this is the B. In a vertical position, this is A and the B. Okay, then let's take these 2 points as A and the B, these 2 points as A dash, B dash. Let's take this is the A dash, B dash. Before it buckle, AB is equal A dash, B dash. Okay, then after buckling, you can see this length has increases compared to AB, but this length has not changed because the neutral layer does not undergo any compression or tension, so that the length remain as same before loading and also the after loading, because this neutral layer not subject to any deformation. Only this A dash, B dash length increases. Okay, increases. So then we are going to find the strain developing this on this layer. Then how to find the strain? How to find the strain? Extend length A dash, B dash minus original length AB divided by original length. This is the basic equation to calculate the strain. What is the strain? A dash, B dash. What is the A dash, B dash length? A dash, B dash from this equation up to this R plus y dash into d theta. From this diagram, what is AB? R d theta divided by original length R d theta. Okay, we can simplify this equation. We are taking the strain as strain is equal y dash divided by r, y dash divided by r. Okay, y dash divided by r. Then if you know the elastic modulus of the material, we can directly calculate the stress developed in this position sigma. Stress is equal E into epsilon, sigma is equal E y dash divided by r. Okay. Then if you take the small area, cross-sectional dA surface area at this point, which is normal to this in this cross-sectional plane on this fiber dA. So what is the force acting on this dA surface area? Let's take the dF force is acting due to this stress. So what is that force? dF force is equal sigma into dA. Let's take the calculation to this position. So then how to calculate the due to this dF force, what is the moment produced around this axis passes through this point? Axis passes through the neutral layer. Okay, what is the dA moment? The dm moment is equal. What is the lever arm? Y dash into sigma into dA. Let me expand this equation. Y dash, what is sigma? Sigma is equal E y dash divided by r into dA. So that the dm we are obtaining, dm is equal to calculate the total moment produced. So we have to integral all over the surface area. So then E is a constant, R also a constant for certain buckling. So y dash square into dA, integral all over the surface area. What is meant by this y dash square into dA? That is the second moment of area of the cross section. So then the total moment we can write that is equal to E I divided by R. Okay. So then we can rearrange this equation as 1 over R is equal m divided by EI. Let's take this equation as equation B. Okay, I think you all got a very clear idea how to obtain this equation B. Okay, that is very clear. So then we are having the two equations. Equation 1. So what is the equation? Sorry, equation A. Here this is the equation A. Here this is the equation B. So then we are going to combine these two equations to form the critical buckling load equation. Let's see how to combine these two equations. From these two equations, from A and B, by equating these two sides, we are getting m divided by EI is equal d2y dx square. Okay, d2y dx square. Then what is meant by this m? Let me take the diagram again. This diagram. So I'll draw it in here. Then this is our coordinate system. Let me draw the beam. We consider this kind of separate beam part for this calculation. this kind of moment is acting on this. This is the moment acting on this M. So then considering the equilibrium of this separated beam part, that means considering the free body diagram of this beam part, all the forces acting on it should be balanced. So then this is the critical buckling load. If critical buckling load is acting in this situation, you can see then let's take this point, the distance to this point as y, length is y. So if you take the moment around this point, if critical into y should equal to m, so then instead of m is equal, if critical into y, so here the magnitude, both the magnitude should be same. That means this moment produced by this critical buckling load is acting in a anti-clockwise direction. This moment we have taken as the clockwise direction. Okay, when you are going to replace this m by a moment produced by this critical buckling load into I, we have to substitute the essentially we have to substitute the its a sign. Okay, so instead of when you are going to put the critical into if critical into y, we have to put the minus sign, because here this m moment acting in a clockwise direction, this one acting on an anti-clockwise direction. So I am going to replace this m with the f critical into y by putting the minus sign. So then we can rearrange this equation. Minus f critical into y divided by ei is equal d2y dx square. Okay. Then by making the minus so I'll make the rearrange this equation. d2y dx square is equal minus f critical into y. Okay, then let's take another better to rearrange this in this way. d2y dx square is equal minus f critical divided by ei into y. The instead of this f critical divided by ei, I am going to put omega square. Okay, omega square. So then this equation we can rearrange this in this kind of manner. The d2y dx square is equal minus omega square into y. Okay, actually what is this equation? Actually this is the, I think you all familiar with this equation when you're doing the A level. This equation I think you may use to solve the simple harmonic motion equation. Actually this is a simple harmonic motion equation. Then what is the solution of this differential equation? It's a differential equation, the simple similar to the simple harmonic motion equation. Then what is the different solution of the differential equation? That means y, how the y is vary. If you can remember in your A level, what is the solution, how you write the solution? A cos omega x plus b sin omega x. Okay, omega x is similar to the simple harmonic motion equation. X double dot is equal minus omega square x. Okay, then you are writing this solution. Xt is equal a cos omega t plus b sin omega t. No. Okay, similar to that one, I will write this equation. Okay, here you can see the a and the b are unknown constant. We have to determine it using the boundary conditions. Okay, then here we are obtaining what we are obtaining in here, the variation of y. What is the variation of y? Let's take this same diagram. This is the buckling way of buckling of the structure. This is the y coordinate, this is the x coordinate. Actually this equation is given how this deviation with respect to the x value according to the length of the column, what is the amount of deviation is given by this equation. Okay, along this x direction, what is the deviation in y direction is given by this equation. Okay, so then a and b constant we have to determine using the boundary conditions. Okay, so what are the boundary conditions? What happen? X is equal 0. What is the y value? X is equal 0. The y is also equal to 0. So then y, x is equal 0, that value is equal to 0. So then here cos 0 means a, sin 0, yeah. So we are getting equation, the a is equal to 0. Okay, a is equal to 0. Then our equation reduces to y is equal b sin omega x. Again we have to determine the b. Then how to determine the b? Okay, how to determine the b? Then you can see, yeah, let's take the length of the column as L. Length of the column as L. Okay, length of the column as L. Okay, length of the column as L. So then y, x is equal L. Y, x is equal L. You can see again the y also equal to 0. Y also equal to 0. So then you can write this equation b sin omega L. B sin omega L. Okay, then 0 is equal b sin omega L. You can see the multiplication of two terms is equal to 0. You can see multiplication of two terms is equal to 0 means either this one equal to 0 or this term is equal to 0. This one cannot equal to 0. This one cannot equal to 0. If this is equal to 0, we don't have an equation. So essentially this one should be equal to 0. That means sin omega t should be equal to, sorry, sin omega L, no, L, sin omega L should be equal to 0. So let me write that equation. Sin omega L should be equal to 0. So what is the omega L value? What are the possible solutions for omega L? That may be equal to 0 or 5 or 2.5 or 3.5. Okay, I'm going to take this first non-zero value 5. That means omega L is equal to 5. So one of the possible solution for the omega L. So then what is the omega? Let me write the omega. If critical EI into square root is the omega, L is equal to 5. Okay, by making if critical into subject, we are getting this equation. 5 square EI divided by L square. This is the equation we are getting for buckling load. You can see the buckling load equation we are getting. This is how we are obtaining this buckling load equation for using the mechanics theory. Okay, I think you all got a very clear idea how to obtain this buckling load equation. Okay. At the same time, I'm going to explain about the lateral support. Okay, this equation further we can expand to explain the lateral support. Okay, here, so what is the lateral support? Earlier we don't have any lateral support. It will before going to this one, let me explain this one. This equation we derive considering the support condition as the both then pin supported situation. Both then pin supported, this vertical movements are allowed situations. Okay, then this equation, let's take similar support condition. Okay, but it having this kind of lateral support at these two ends. Let's exactly at the middle. Let's assume it having exactly at the middle. Okay, but it allow the vertical movements. Then how in this situation, how the structure buckle? Okay, so I will draw the line element for this to explain this one. Let's take this the structure. Okay, when it buckle, it will form this kind of curvature. When it buckle, it will form this kind of curvature. Okay, because there's a lateral support in here. Because it having lateral support here, then it cannot produce this kind of arc when it buckle. So it form this kind of buckling. Okay, in this situation, how this equation we can rearrange? How the equation can rearrange? In this situation, you can see another boundary condition has developed. That means total length, let's take it as L. At L over 2, at x is equal L over 2, y goes to 0. Y is equal to 0. So then let me substitute this equation in the previous value. Okay, in here. Okay, so that means sin omega L divided by 2 is equal to 0. That means omega L divided by 2 is equal to 5. Okay, then if we rearrange this equation, if critical divided by ei square root L divided by 2 is equal to 5 means, then if we, by making the f critical into subject, we are getting 4 5 square ei divided by L square. You can see, if you can give the lateral support to the structure, the critical buckling load increases the 4 times. Okay, critical buckling load increases the 4 times. Okay, 4 times. Here without buckling load, here with the without lateral support, here with the lateral support. So what happens if you give the 3 lateral supports in equal distance? If we give 3 lateral support in equal distance, so how the structure fail? How the structure buckle? It will buckle from this kind of manner. So you can see the two boundary conditions have developed. That means x is equal L over 3, y is equal to 0. So then we can write the sign omega L over 3 is equal to 0. So then if we obtain the critical buckling load in this situation, we are getting 9 5 square ei divided by L square. 9 5 square ei divided by L square. You can see in this situation, if we can give the 2 lateral support in equal distance, we can increase the buckling load in 9 times compared to the without any lateral support. Okay, this is for the both 10 pin supported structures. Okay, I think you all got a very clear idea how to obtain these equations. Okay, further let me explain for different support conditions. Further let me explain for the different support conditions. Here we consider both 10 pin support situation. Let's take the situation. Okay, let's take first one. Both ends pinned. pin supported, both end pin supported. In this situation, what is the equation we obtained? Already we obtained this one. If critical buckling load is equal 5 square EI divided by L square. Okay. Then another situation, here it is the fix, then this one is the free end. Okay, one end fix and one end free. In this situation, it will buckle forming this kind of curvature. Okay, in this situation, it will buckle forming this kind of curvature. The buckling load is equal, critical buckling load is equal 1/4 5 square EI divided by L square. So then another situation, the two ends are fixed, both the ends are fixed. So then in this situation, it will form this kind of curvature, buckle. And fixed support. In this situation, the critical buckling load is equal. 4 times 5 square EI divided by L square. So then another situation. Let's take another situation. The one end is fixed and other end is pin supported. Load is acting. So in this situation, it will form this kind of curvature. So in this situation, the critical buckling load is equal to 5 square EI divided by L square. Okay, you can see when we are in the support condition, the buckling load also vary. We derive this equation for considering this situation. Then other situations we are not going to derive in this lesson. Okay. Then the person who invented this theory and equation called the Euler. Person who invented this equation in 1750, around the 1750, the person who called the Euler. Okay, I think this is the equation. This is the oldest equation is still using in engineering field to calculate the structural strength against the buckling. This is the oldest equation. This is the oldest equation is still using for engineering applications. The person who invented this is Euler in 1750. To gratitude him, we are calling this equation as the Euler buckling load equation. We are calling this formula as the Euler buckling load formula. Okay, Euler buckling load formula. Okay, enough for today. Let's continue next day class. Okay, thank you.